Hello, my name is Asma Guemoula. I am a PhD student from Hamal Akhdar Al Wad University, Algeria. I will talk about some inequalities for bounded linear operators in the new norm on pH. Book plane, 1 abstract, 2 introduction, 3 preliminaries, 4 main results, 5 references. Abstract. In this presentation, we study some important properties for the alpha-beta norm newly introduced in reference 12 and obtain upper bounds for the said norm on the space of bounded linear operators on complex Hilbert space, from which we obtain bounds for the numerical radius of operator. Some other results are also given. Introduction. Let pH denote the C star algebra of all bounded linear operators on a complex Hilbert space H with usual linear products. An operator T in pH is called positive if this for all x in H. For T in pH, T star denotes the adjoint of T. The numerical range of T denoted by WT is defined by this. The numerical radius omega t is defined as the radius of the smallest circle with centered at the origin and containing the numerical range is defined by this. In reference 12, a new norm named alpha-beta norm on pH for T in pH. The alpha-beta norm of T denoted by that is defined as this. Where alpha-beta are real positive constants with alpha-beta are not nil, we know that if alpha equal 1, beta equal 0, then alpha-beta norm of T equal omega T, and if alpha equal 0, beta equal 1, then alpha-beta norm of T equal norm T. Also, if we consider alpha equal B equal 1, then we have the modified Davis-Wieland radius of T that is equality. See reference 3. The organization of the work is as follows. We present some results on the important properties for the alpha-beta norm and upper bounds for the said norm, from which we obtain bounds for the numerical radius of operator. Some other results are also given. Preliminaries. We present here some lemmas and corollaries which are useful for show our result. Lemma 1. The following inclusion relations for the classes operators as it shown. Lemma 2. Let A be E in H with norm E equal 1, then we get this inequality. Lemma 3. Alpha-beta norm defines the norm on pH for alpha-beta are positive such that alpha-beta are not nil and is equivalent to the numerical radius norm omega and the usual operator norm satisfied in the following inequalities. Lemma 4. For A, B are positive and alpha between 0 and 1, then we get this inequality for R big and equal 1. Lemma 5. Let A in pH and A are positive and let X in HB and in unit victory, then we get the inequality 1 for R is big and equal 1, and we get the inequality 2 for R between 0 and 1. Main results. We present some results on the important properties for the alpha-beta norm and upper bounds for the said norm, from which we obtain bounds for the numerical radius of operator. Some other results are also given. Remark. Let I is an identity operator. We can verify that this equality, where alpha and beta are positive, which alpha beta are not nil. And if alpha plus beta equal 1, we find alpha beta norm of A equal 1 equal norm A. Proposition. The alpha beta norm on pH satisfies the following properties. 1. For any lambda in complex space, then we get this equality. 2. If UEPH is an unitary operator, then we get this inequality. Proof. For every bounded linear operator, T defined on complex Hilbert space from the definition of alpha beta norm, where alpha beta for non-negative real scalars, alpha beta are positive such that alpha beta are not nil. 1. Let lambda in complex space, we have this equality. Clear. 2. Let U in pH is an unitary operator. By using some equalities and inequalities, we get the required inequality. Theorem 1. Let T be a normal operator in pH. T star its adjoint. Then we get this equality where alpha and beta are positive, which alpha and beta are not nil. Proof. Let T is a normal operator using the definition of the alpha beta norm and some inequalities we have. On the one hand, we get these inequalities. Proof. By using some equalities and inequalities and lemma 1, on another hand, we get these inequalities, so we get the proof. Theorem 2. Let T as R in pH such that T commutes with S and R. Then we get these inequalities where alpha and beta are positive, with alpha and beta are not nil. Let X in H norm X equal 1 using the definition of the alpha beta norm and lemma 2, we get the proof of the previous theorem. Using the previous theorem, we get this corollary. Corollary 1 using equation 1 and lemma 3, namely this equality, we obtain the following inequality. Theorem 3. Let A be X in pH such that A and B are positive, then we get this inequality where lambda are between 0 and 1, which alpha and beta are positive, and alpha and beta are not nil. Proof. Let X in H be a unit vector by using the definition of the alpha beta norm and the equalities and inequalities and lemma 5 and lemma 4, we get the proof of this inequality. Corollary 2. Let lambda tilde be the generalized alleged transformation of T such that U is the unitary, which the polar decomposition of T. Then we get this inequality where lambda between 0 and 1 with alpha and beta are positive and alpha and beta are not nil. Proof. If we take A equal will be equal absolute value of t and x equal u in theorem 3. By using some simplification, we get the required equality. References. These are the references which we use to get these results. Finally, thank you for your attention.